Hi, everybody. My name is Michelle Ntampaka. I am delighted to give this talk today and to share with you some thoughts about machine learning for cosmology. And I want to start with a little bit of a bold statement, and that is that I believe that astronomy is the ideal sandbox for machine learning. Why do I think that? We have minimal privacy concerns. So someone who might work in something like health records would be very concerned about protecting the privacy of the person behind the data. For astronomy, our photons carry no privacy, and so this is just not something that we have to worry about. Astronomy has a culture of collecting these big and expensive data sets and then sharing them widely with the community. Our surveys are rich with information. We have well-posed questions. Astronomy enjoys public interest and public support. And our data are worthless. They are non-monetizable. You cannot use them to sell something new. And while that doesn't exempt us from ethical concerns, I think it does make astronomy just one of the best places to do data science in general and machine learning in particular. But one thing I think we need to wrestle through is the question of, is machine learning the right tool for astronomy? On short timescales, we need to be asking, can machine learning be trusted? So right now we should be assessing our models and trying to identify if these are trustworthy models or if we should be suspicious of the results. On longer timescales, say the next 5 to 10 years, we should be looking at whether machine learning can be used to make new physical discoveries. And then even farther out, we should be exploring what role will machine learning play in the future of astronomy. So these are the three questions that I'm going to explore today. With these first two, I'm going to look at a very particular case study. So this is a case study in interpretability. We're going to look at galaxy clusters as a cosmological probe. So galaxy clusters are the most massive gravitationally bound objects in the universe. And here you are seeing a composite image of the Virgo cluster. You're seeing it both in optical and in X-ray. So in optical, you're seeing the rich collection of hundreds to thousands of galaxies that live in galaxy clusters. And in the X-ray, that's the purple overlay, you're seeing the hot intercluster medium that is glowing primarily through thermal bremsstrahlung. For this case study, we're going to be looking just at X-ray, and we're going to be exploring the S8 tension. So the S8 tension is an open question in the modern cosmological model, and effectively, cosmological microwave background measurements predict that there should be more massive structure, as you see in green here, compared to measurements of large-scale structure. So these early time up at the top, the Planck CMB ones, early time measurements in green, predict that there should be more massive galaxy clusters than probes of large-scale structure C. And those are the measurements at the bottom. And while these are not a significant tension, you can see that it's a persistent tension. Our measurements of large-scale structure regularly do see fewer galaxy clusters than the CMB would predict. The way we can use galaxy clusters as a cosmological probe is by looking at cluster abundance. So here what you're seeing is, as a function of mass, the abundance of galaxy clusters predicted for a number of different sigma 8 values. So sigma 8 is a measurement of the clumpiness of the universe. And for a low sigma 8, that's the solid yellow, you'd see many fewer galaxy clusters. And for high sigma 8, here I'm showing that in the blue dash dotted, you'd see a much larger abundance of clusters. So it's really sensitive to the underlying cosmology. So the game is, if we can measure up the abundance of clusters as a function of their mass, we can use that to constrain cosmological parameters. However, we just talked about sort of the sigma 8 effect, but now I want you to take one of these lines in your head, maybe take the green dashed line, for example, and imagine, rather than a change in sigma 8, which to 0th order looks like sort of an up-down shift, imagine we had some uncertainty in mass. which to zeroth order would look like a right-left shift. You can see how these two things are degenerate. It can be hard to tell them apart. Now, weak lensing masses can help us with that mass calibration. For this case study, I am using simulated galaxy clusters. They are from the Magneticum Cosmological Hydrodynamical Simulation. This was run at a low sigma 8 cosmology, one of the ones preferred by probes of large scale structure, the WMAP7 cosmology. Magneticum is a really nice sim for these kinds of studies because it's large enough to produce a realistic and a diverse population of galaxy clusters, but it also has the resolution and the hydrodynamics to be able to make these X-ray mocks, as you see in the bottom. For this work, we're doing something. We're doing mocks that would be, as you would see clusters, clusters as they would be seen by the Chandra X-ray Space Telescope. So in order to pursue this study where I'm going to be looking at populations of clusters and trying to identify the underlying cosmology, I need to build many cosmologies from one simulation. At the high mass end, those are going to follow a volume limited sample. So what you're seeing in this entire figure right now is a volume limited sample of galaxy clusters as a function of cosmology. At the low mass end, however, an X-ray survey will be flux limited, meaning you're only going to catch the brightest objects. So you're going to tend to see a mass function that looks like this. You've got a volume limited sample at the high mass end, a flux limited sample at the low mass end, and they stitch together at some point in the middle. There is some uncertainty of where they will stitch together. So you're actually going to end up with a really diverse set of possible halo abundances for these many different sims. It's going to look something like this. So quickly to summarize, a typical X-ray survey will include both flux and volume limited regimes, and also uncertainty in the mass at which these two join. For this work, I'm going to be putting my simulated cluster samples into a 2D array. So I've shown a couple of examples here on the right-hand side, but let me talk you through what each of these are. Each pixel in this 2D array is a cluster observable. That's going to be something like a cluster temperature, a cluster gas mass profile, a cluster gas density profile. Cluster information is arranged in a row. And each of these 2D arrays or images is a full simulated cluster sample with the most luminous cluster at the bottom and the least luminous cluster at the top. All right. So you can see these samples here for a number of different S8s or sigma 8s. They're going to produce different abundances of clusters with different observational parameters. So to quickly summarize here, we have simulated realistic cluster samples for many cosmologies and have cast each into a 2D array. Let's now talk about the machine learning tool and the approach for this. We're going to start by talking about neural networks. So a neural network is a deep learning technique that can be used to approximate any function. So here, I've shown a function that has 9 input parameters. Those are in white on the left-hand side. 3 hidden layers, those are in green, and a single output that's in purple on the right-hand side. And what's going to happen is a neuron in one of the hidden layers is going to be a linear combination of the neurons in the previous layer with a nonlinearity folded in on top. And we are going to learn the weights and the biases in order to be able to take this training data from my 9 input, 1 output arbitrary function and be able to approximate it. So moving down, each of these neurons is going to be a linear combination of the previous layer. Similarly, with my second hidden layer, we're going to do the exact same thing. All right, moving up a little bit in complexity, now let's talk about autoencoders. Autoencoders are a type of unsupervised learning, meaning you don't need to have sort of the right answer or the label. in order to be able to run an autoencoder. This autoencoder takes a signal with nine measurements or 9 parameters, a 9 parameter signal. It bottlenecks it into a single summary and then attempts to reconstruct that exact same signal. There's no reason why the bottleneck should be a single value. You can choose any arbitrary number of values. If you want to think a little bit more about an autoencoder, your brain is actually quite good at this. This is just a flexible version of principal component analysis. But think about maybe a Gaussian function. You may have a lot of measurements that describe that Gaussian, but ultimately your brain simply needs to know where the mean of the Gaussian is, what the standard deviation of it is, and what the amplitude of it is. With those 3 parameters, you can reconstruct the Gaussian. So we're effectively doing the same thing. This is about to get more and more complicated, and so I'm going to abstract away those hidden layers and just represent them as sort of these solid triangles. For the work I'm doing, I've built a supervised encoder. This is engineered to mimic a human approach to the task of cluster cosmology. So I've got my input. In that input, I've got my list of galaxy clusters. Remember, each cluster lives in a row in the input. I then have an encoder. You can see in the slice of solid green, my encoder acting on a single galaxy cluster. It's going to take that cluster and it's going to summarize it as a single parameter. I'm going to call that parameter the Terse value, but you and I both know that it's a mass proxy. We're taking those cluster observables and we're going to turn it into the cluster mass. Now I've got a list of these Terse values, and I'm going to take that ordered list, crank it through a CNN, and ultimately output the underlying cosmology. Okay, so to repeat it one more time, because I think this is really important, the encoder is going to mimic a human approach to the task. We're going to take the cluster observables for each cluster, make a cluster mass proxy. Then I'm going to take a list of the mass estimates and use that to constrain the cosmology. What do the results look like? Here, I'm showing, this is for the simulation that I talked about earlier, the Chandra mock X-ray observations. On the x-axis, the true sigma 8 of the simulated sample I put together. On the y-axis, the predicted value from training this encoder. And you'll notice a couple of things. The first thing you'll notice is there are some substantial error bars here. We're working with really small cluster samples. And so my error bars are at the size of about the expected theoretical limit for how well we can constrain with these small samples. The second thing you're going to notice is that at the really low and really high sigma 8 end, we are biasing toward the mean. So you see it kind of folding down at the top end, folding up at the low end. This is a known problem with many machine learning tools that interpolate better than they extrapolate. As the model is training, because it never sees sigma 8 values lower than 0.7 or higher than 0.993-ish, it's never actually going to estimate a value lower than 0.7 or higher than 0.93. So that's why you see this sort of tilting toward the mean. In practice, what you're going to want to do is build a training data set that extends well beyond what you think the underlying truth is, so that you're working in the middle part of that regime where you've got really a lot less bias in your results. Okay, with the results out of the way, we're now going to get to the important work of interpreting it. I think this question, can we interpret and understand and make some sense of what our machine learning model is doing? This is really important. And I think it's going to become more and more important as the field embraces machine learning. So this is where I want to spend the bulk of the time. Remember, we're exploring on really short terms the question, can machine learning be trusted? And on longer terms, on longer timescales, can it drive physical understanding? And I'm going to address both of these. The first, we're going to look at terse value correlations. We'll use that to assess whether the model will generalize. That can help us build trust in our machine learning models. The second thing I'll look at is saliency maps. That'll help us to identify what part of the cluster carries the most cosmological information, and that can lead to machine learning driven discoveries. Okay, let's look at the first one, correlations to trust. The big idea here is we're going to visualize how the terse layer correlates with cluster parameters. As a quick reminder, I'm showing the architecture on the right-hand side, and the terse value, as we know, is going to be something like a mass proxy. This is going to help us build trust by asking, is the terse layer summarizing sensible features? So let's go ahead and visualize how the terse layer correlates with cluster parameters. We're going to look at it for two sets of data. On the left-hand side, you see what I'm calling the trustworthy results. These are the results that I showed you earlier. I told you that these have error bars at about the expected theoretical limit for my data set. On the right-hand side, I'm going to show you another model that I trained. And I woke up, I took a look at these results that had run overnight, and I was incredibly suspicious. They are a factor of 10 better in error bars. There are error bars, they're just hidden behind the points. You see virtually no bias toward the mean. They are better results than the expected theoretical limit by a factor of 10. And before I published this, I really needed to understand, are these results trustworthy? Have I built a tool that truly does a factor of 10 better? Or has my model cheated? So the first thing we should look at is correlations with mass. So here you're seeing on the x-axis, the terse layer value. This is a unitless quantity, so don't pay too much attention to the actual numerical values there. All right, the terse layer value, remember this is the machine learning's version of a mass proxy. And on the y-axis, the mass, the true underlying mass. We're seeing just a two-dimensional histogram. In the trustworthy results, my machine learning model has built a mass proxy. You can see that these are tightly correlated. On the right-hand side, my terse layer value is uncorrelated with mass. And this is a red flag to me. This tells me that there's something underneath the hood that is not right about this model. This deserves some more attention. The second thing we can look at is correlations between the terse value on the x-axis and the underlying sigma 8 on the y. In practice, you should not be able to tell the underlying sigma 8 from a single cluster measurement. That should be completely impossible to do. So my terse layer value should be uncorrelated with sigma 8. And in my trustworthy results, that is in fact the case. On the right-hand side, for my suspicious results, you see the terse layer value is strongly correlated with sigma 8, and this is the problem. The model picked up on a cosmology-dependent simulation artifact. The thing cheated. And from finding this sim artifact, it was able to infer sigma 8 from just a single cluster. Will this extend to actual observations of the universe? Absolutely not. Unless the universe has the same simulation artifact as the data set I put together. This is not a thing that will extend. So now I've been able to figure out what's going on. The verdict? For the suspicious results, machine learning cheated. These results are not robust. The model will not generalize to real observations because it depends on a sim artifact. Let's now take a look. Let's summarize here quickly. The terse value correlations, we visualized how the terse layer correlated with cluster parameters, and that helped us to build trust in the model. We were asking, is the terse layer summarizing sensible features? We found in one case it was, but in a second case, it was not. It was cheating and had identified a SIM artifact and was using that. Now let's ask the question about machine learning for discovery. We're going to look at saliency as a tool for leading to discovery. The big idea here is we're going to assess the importance of each cluster feature by looking at gradients in the encoder network. We're going to ask, how does changing the input value change the terse value? And this will help us to develop a physical framework for understanding surprising results. I want to start this conversation with a picture of a horse, and I want to ask you, how can you tell that this is a horse? And how can machine learning tell that it's a horse? Okay, I know you're watching a recording, but take a pause here and think about how you would answer this question if you needed to answer it verbally. There was a really interesting paper that explored machine learning image recognition and looked at the relevant features for each class in their data set. And they found a surprising result for horses. The ML was not paying attention to the color of the horse. It was not looking at the shape of the head or the tail. It wasn't even looking at the green background and the picket fence. It was looking for the existence of a copyright stamp in the lower left-hand corner of every horse image in their data set. So it turns out that when the data set was built, all the horse images were contributed by a particular photographer. Here's a figure from that paper. In the top left-hand corner, you see the picture of the horse with the copyright stamp. And next to it, you see a map that shows how important each of these pixels are for the final decision. And you see that the horse there, the copyright stamp is really lighting up there. When they removed the copyright stamp, the algorithm no longer classified this as a horse. Even more concerning, they took this artificial picture of a car, added a copyright stamp, and their algorithm, with confidence, classified this picture as a horse. Why are we talking about horses in the middle of a cosmology conference? It's because if machine learning has this tendency to cheat, if it will hook into things like simulation artifacts or other undesirable features, we as cosmologists need to know. We need to be able to treat our expensive data with an appropriate amount of respect and pair it with a model that is appropriate for the task. We need to be able to look for and find these cheating behaviors. In my model, I did explore a similar question, looking at these saliency maps. What's the most important feature? As a reminder, I've got temperature, gas mass, and gas density profiles are my columns, and each row is a single cluster. It's hard to extract information from the saliency map I'm showing on the right, but fear not, because this is ordered data, we can make some sense of it. So I'm just going to summarize some of the saliency here. So here what you're seeing is a summary of that previous figure. On the x-axis, cluster log mass. On the y-axis, a measure of saliency for a particular gas mass in two cases. Toward the bottom, that solid thick teal line, this is my standard case. Right? In this case, I've given the machine learning temperature, gas mass profile, gas density profile, ordered by luminosity, and I've also fed in at one point the weak lensing values of each of my clusters for that mass calibration. And you can see that my model is paying roughly equal attention to every gas mass or every cluster mass. Okay, it's pretty flat. When I remove weak lensing, when I take away its ability to really calibrate the masses, something interesting happens, and that is that it starts paying attention to the middle mass regime, somewhere around 14.2, 14.3. It's really looking there. It becomes very sensitive to those masses. It turns out that this middle mass range correlates with the place that we saw earlier, the transition range between the volume limited and the flux limited samples. That's what I'm showing here in blue, is that transition range. So it seems like it's paying attention to this transition. This is really interesting. This deserves a little bit more attention. So what we did, actually, let me summarize here first before I tell you what we did. We were, after seeing this kind of smoking gun plot, we started to suspect that the model is finding the transition point between the flux and volume limited samples, and it was using that to calibrate cluster masses without weak lensing. Said another way, here I'm showing for my cluster samples the number of clusters on the x-axis, the median yx on the y-axis. Okay, yx is a mass proxy. It is observable. It correlates with the place where you're transitioning between the volume and the flux limited sample. So this is an observable way of finding that transition point. So what we're seeing is number of clusters in the sample, median yx. Then the colors there are the average sigma 8 in that bin. I've highlighted two sections, A and B, those boxes A and B. So in box A, you've got in the X and Y axis, or in the X and Y direction, roughly the error bars that are measurable. And then you can go to the pop-out box at the top. And you can see that in box A, our distribution of sigma 8s centers around 0.74 with a scatter of about 0.03. For box B, we have the same scatter, but we have a very different median sigma 8. Said another way, if you were given a number of clusters and a median yx, you could use this figure to estimate the underlying sigma 8. Of course, it's going to be survey dependent. If you have a smaller volume or a larger volume, you're going to get different distributions. And so this needs to be forward modeled. However, this is effectively a self-calibration mode that we can use for observations for X-ray surveys, like the one that is currently being performed by the eROSITA X-ray telescope. So to summarize here, we talked about looking for physical understanding with ML, and here we use Saliency Maps that allowed us to assess the importance of each cluster feature by looking at gradients in the encoder network. Said another way, we're asking, how does changing the input change the Terse value? This allowed us to develop a physical framework for understanding surprising results, and ultimately led to the discovery of a new and previously unknown self-calibration mode. Okay, now let's look ahead. What role will machine learning play in the future of astronomy? I really believe that astronomy, machine learning and astronomy can and should move forward together. Here what I'm showing is, as a function of year, ImageNet competition results. So ImageNet is an image classifying competition. And you'll see a surprising outlier in 2012, that really low error outlier at about 15%. This is AlexNet. This is the first convolutional neural network to be really successful in this competition. And you can see in previous years, lots of folks jumped on the convolutional neural network bandwagon. And this was a really big leap in image classification techniques. Cosmology has well-defined problems and really interesting data sets that can allow machine learning to build new algorithms to address them. So I really think there's an opportunity here for a synergy for ML and astronomy to move forward together. To address this, I want to talk to you about a program called Hello Universe. Hello Universe, the website is at the bottom of this page. Hello Universe is astronomy data sets paired with pedagogical Jupyter notebooks for teaching and benchmarking machine learning. So a novice machine learner can use Hello Universe with the notebooks to learn new techniques. An expert machine learner can use those Hello Universe data sets for benchmarking new algorithms. This is what our webpage looks like at the moment. You can see we've got a nice variety, both of types of data and also algorithms used on those data. So I really encourage you to check those out if you're interested in ML for astronomy. We also have these beautiful, rich upcoming data sets. Rubin and Roman and eROSITA, all collecting large data sets with rich effects of physical processes that will allow us to really explore data with ML. So I'm really excited about these three in particular. On the technique end of things, there are new techniques in ML that I'm just really enthusiastic about, and I want to highlight a couple of them. The first one is style transfer. You see an image on the top left, and style transfer can be used to take the style of another image, in this case, a couple of famous paintings, and reimagine that image of houses as it might be painted by Van Gogh, for example. Why am I talking about this in an astronomy talk? I could imagine us using a similar technique on simulations. Imagine you've got a simulation and now you want to change some of the hydrodynamical parameters underlying. Could we use ML to do that and save time and computation? I don't know the answer to it, but it's something that I'd be excited to explore. Another technique I'm really excited about is super resolution. Here I'm showing a figure from a paper about pixel recursive super resolution. Given the image on the left, the model produced the image in the middle column, and the one on the right is the underlying truth. Now, I do have to emphasize here that the model knew it was looking at a picture of a face. So it was trained on face priors. You cannot get something from nothing. And this model knew that ultimately it was expecting something that was arranged like a face. All right, so you cannot just turn it and train it on. You could not take this model and use it to predict something else entirely. You would get nonsense. But this is really exciting, imagining something like a low resolution image of a galaxy and looking for techniques that might allow us to explore realistic high resolution images of that same galaxy. Now, you do have to be aware of underlying biases. If your data set is biased, your results will be biased. I show this for two reasons. So reason number one is I want you as astronomers to have a case study or a quick visual of what can happen if your training data only include a subset of the real distribution. The second reason I show it to you, though, at the beginning of this talk, I said that as astronomers, we are not exempted from ethical concerns, but the space that we work in has a lot of freedom. We do, however, have to be thinking carefully about our trainees and make sure that if we are preparing trainees who are going to go out and work in industry, that we are helping them to think carefully about the implications of the research that they do, how it might be used, and how it might be misused. We want to prepare them to look for things like this. Another bias that you should be aware of, or that I'd like to talk about here, ML bias in language translation. So Google Translate, when translating from Turkish, which I am told is a gender-neutral language, will take the sentence on the left and translate sentences on the left and translate them as, he is a doctor, she is a nurse. So again, we are seeing the existing bias in language being picked up by ML. Another thing we need to be thinking about for student trainees in our group is to be aware of places where one might automate human biases. So you may have heard about Amazon's AI tool for recruiting. Effectively, what they did is they took resumes of their of engineers who had been successful at Amazon, and they used those for training an AI that would be able to sort through resumes and identify promising new candidates. What the algorithm actually did was it learned to look for men, and in particular men from high socioeconomic backgrounds. So if the algorithm identified anything about a resume that indicated that the candidate was a woman, or that the candidate came from a low socioeconomic background, it downweighted that candidate. Ultimately, Amazon scrapped that. But this is, again, another thing we need to be talking to our trainees about and make sure that they are aware that machine learning tools can latch on to things that we don't want them to latch on to, and they should be used with care, especially in these kind of spaces where we're making decisions that affect people's lives and livelihoods. Another one I want to talk about is toward the beginning of the pandemic, there was a lot of interest in using image recognition for identifying from a chest scan whether a patient had COVID or pneumonia or was healthy. Ultimately, hundreds of AI tools were built to catch COVID and none of them helped. What were these algorithms doing? Early data sets included patients who were lying down and standing up. Patients are more likely to have a chest scan performed lying down if they're very ill. The algorithm learned that if it could figure out that the patient was lying down, the patient likely had COVID. Early data sets included a combination of adults and children. The algorithm learned that early in the pandemic, it was unlikely that a child was COVID positive. Therefore, a pediatric patient was likely going to be COVID negative. And I think that the funniest thing that these algorithms did was actually identifying the fonts used in the chest scans at hospitals in hotspots toward the beginning of the pandemic, and learning to correlate the fonts with the likelihood that the patient had COVID. Okay, said another way, machine learning is really good at picking up on things that we do not want it to pick up on. And we need to be careful, and we need to use assessment tools to understand how well our algorithms are working and what they're seeing. So let's return to the original question. Is machine learning the right tool for astronomy? I believe that machine learning can be the right tool for astronomy if we do some things. If we engineer models that follow a human approach with checkpoints to make sure that the model is learning something sensible. If we interrogate and interpret our models. If we approach high accuracy results with scrutiny, and if we treat machine learning as a tool that can be used in partnership with traditional statistics, traditional statistical methods, and human exploration. So today we explored 3 big questions, and this final slide points you to some resources that I used for building this talk. So we looked at the question, can machine learning be trusted? Can it drive physical understanding? And what role will machine learning play in the future of astronomy? I am really looking forward to the discussion and chatting with you all about the things from this talk. Thanks very much for listening, and I will see you soon.